February, probability theory. Okay, so let me recall. So uh, I introduced the notion of discrete random variable, discrete, and continuous random variable. Random variables. We also had this notion of mass function, mass function, also called a probability mass function. Some people write probability mass function and even abbreviated to PMF, and also the notion of density function, F from real numbers to 0 to infinity, or real numbers, you can just write something here. And this is for discrete, and this is for x continuous. Yeah, so um, in my definition, I just said that mass function is defined only for values x1, blah, 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 xn or something. But you can just define, yeah, sorry, I wanted to say something else. Yeah, so in my last lecture, I might have written 0 to 1. That is wrong. It's actually going from 0 to infinity. Of course, if you are working with mass function, you can say f is from real numbers to 0 to 1, if this is a mass function, for a mass function. Okay, and of course, you have f of x1. See, suppose x takes values only x1, x2, x. So this is for mass function. So that will always take values from here to here. I even made the domain equal to this, but it's better to have the domain equal to whole of R, where just, well, I mean, you can, if x is not one of these xi's, then set it to be equal to 0. You can take that convention, but it really doesn't matter. What is important is to understand the distinction between the two. Okay, so what is the density function on the other hand? Let me recall for you. Density function here is from f from real numbers to 0 to infinity. For x continuous random variable, and fx of x is given by integral minus infinity to x f of x dx. Okay, so yeah, this is what is required of this. If you take a discrete random variable, it is not going to be continuous. You will not be able to find a function. I said integrable function. Let us not try to make this notion very precise, but uh, continuous functions with compact support are definitely integrable, and so on. So you will see plenty of examples later on in the course. At the moment, just something for which you can make sense of this, and it turns out to be a finite number, and that number must be between 0 and 1. So that's the thing. And of course, f of x must be greater than or equal to 0, as always. And yeah, so that is the thing. The problem is that you will, for a, if, so these two are qualitatively very different. you will not be able to write a discrete random variable, the um, distribution function of a discrete random variable in terms of an integral. It's simply not possible. Even if you make the domain to be whole of R. In my definition, I wrote domain to be maybe x1 to xn, but it doesn't really matter. You can put extend it by 0 outside of this set. Even when you do that, you will not be able to, when you do this, apply this definition blindly to a mass function, you will always get the whole integral to be 0, because it is 0 outside a finite set of points, and therefore when you put the integral minus infinity infinity fx dx is going to be 0. So these two are very different type of objects. And you can have a mixture of this. I was trying to draw some diagrams and so on, but we will today see many examples. So having pointed out the qualitative difference between the two, so you can of course have a mixture of this. X can be X can be of mixed type. Okay. So that's another possibility. We have not done examples. We will do examples in a minute. And besides these, there are also, I talked about this X can be singular, and I don't want to expand this. Okay. So this is a random variable which is neither discrete nor continuous. So you cannot write like this. Discrete, I told you how you should imagine. You have these points x1, x2, xn. So on these, some weightages are associated, and they are just probabilities p1. So you just think of them as atoms with mass p1 to pn. Of course, summation pi must be equal to 1. So that is discrete, and it can be partly discrete, partly continuous, but it can be something which is neither discrete nor continuous nor of mixed type, and those are, captured by the notion of singular random variable. We will not talk about that in this course. And a general one can be a mixture of both discrete, continuous, and singular. That's the most general one. Okay, so let us do some examples. Okay, so I want to give an example of mixed type. Um, so, you think of the following experiment. So, uh, toss a coin, and observe the outcome. So, if the outcome is heads, then pick a point in the interval 0 to 1. Okay, and so this is the experiment. So if the outcome is, I'll switch off now. Sorry about that. The outcome is tail, then toss a coin again. Okay, and observe the outcome. That's it. So this is the experiment. So what is the sample space in here? Omega is either tail or tail h and union. So H, sorry, I said H and wrote T. So H, it's a pair, H comma X, and X is in the interval 0, this and this. And what is the probabilities associated with this? Suppose a coin toss, of course the same coin is tossed. Okay, probability of H is equal to P, probability of tail. Probability of tail equals, of course, Q, which is 1 minus P. We have been using this notation. And what about probability of, okay, so choosing a point belonging to an interval. So that is, let us say, uniform probability. And that means that, so probability of an open interval, A comma B, or closed interval, it doesn't really matter, is B minus A. Okay. This will be a real number again between 0 and 1. And yeah, so B less than A. Sorry, A less than B. And this is between 1 and 0. And we don't care to say what are the, I mean, full collection of script F. That doesn't matter. These things sort of define it. And yeah, so what about something like this, TT, and so on? Just for the thing, I'll explain. So this is Q times Q, of course, and probability of TH, this is PQ. And what about probability? So this is the probability on omega. So these are sort of for individual components, and probability of, let us say, so H, X, so this set consisting of pairs HX, where A less than X, less than or equal to B. Okay. And it's understood that A and B are between 0 and 1. And this is equal to, so let us say, P times, okay, B minus A. And so now you can check that, so what is the total space, and compute the probability, and it will turn out to be equal to 1. Let me not do that simple calculation for you. Because you see, for the total space, what is this? X can be between 0 and 1 here. So 0 and 1, and then if it is H, then it is P. Okay. So and you add up all this, P plus PQ plus Q square. So that becomes Q times P plus Q plus P, which is, of course, 1. All right, now what is the, we can draw the graph of, so what is fx here? How do you compute it? Fx of t. Mind you, fx is a map from where to where. So this is just to remind you, R2, 0, 1. Okay. So if you know that, if you make some calculation and if it turns out fx of t goes outside this range 0 to 1, you made a mistake somewhere or the other. Okay, so uh, so this is equal to, just write the definition always. This is a probability of your set omega. So we just briefly write x omega is less than or equal to t. Okay. Now several possibilities. T is less than 0. If t is less than 0, okay, you can check this. This is an empty set, so this is 0. Less than or equal to 0, well, we'll see.
So what is the random variable here?
I have not defined it. Absolutely. That's, sure. Okay. I went a little bit further ahead. So I'll define the random variable. That's absolutely correct. I need to define the random variable. Okay, so before I do this, let me define the random variable here and make it into a problem where, what is a random variable x? So that is from omega to uh, real numbers, right? So omega, so x of tt, so it takes a lot of time to write it. Let us say x of t, comma anything. Okay, let me write here. Yeah, tt is equal to -1. x of th is equal to, let us say, minus half. And unfortunately, I have to go to the next page. X of x, so x of h, and now I'm going to write here a variable. So I will write product notation. I hope it's clear what I mean. This is equal to a comma b in this interval. Okay. Uh, Let me not write this. Hmm. So x comma, so h comma x. I should write this. Is an element of that. This is equal to, now this little x, if you find little x confusing, I'll write omega here. There's going to be some more x. So let me write omega here. And omega is an element in this interval. Okay. So let us say it is p times, okay, just doesn't matter what p is. So let us just write here x. Yeah, sorry, omega. Ah, omega. So this is it. Okay. So mind you, omega is a real number between 0 and 1. That's in the definition of capital omega. So when the first coordinate is h, second coordinate takes values between 0 and 1. So I just write here omega. Okay. And now what is fx? So we have to compute ft. So ft, I write quickly. Hope I don't make mistake. So this is equal to 0 if t is less than or equal to, if t is strictly less than, not less than or equal to. It's very crucial here. Strictly less than minus 1. And when t equals minus 1, what do you get? So when it is minus 1, notice that this always takes values in the interval here, I mean 0 to 1. Okay. Okay. So if t is minus 1, only it could have come from here. Okay. So if this is probability of x omega, I confused notation, I should have used x. What are all the elements of this sample space so that this is less than or equal to t, less than or equal to minus 1. Minus 1 occurs here for exactly 1 point, that is tt. So it is q square. Okay. And it is remaining so, in fact, minus 1 less than or equal to t less than minus half. The moment it is equal to minus half t, so minus half less than or equal to t and less than 0. This is both th and tt will come, okay, because they are in this range. So there it becomes, okay, you just have to add these two probabilities, because you see th is q square, tt is q square, th is pq. So if you add it, you will get q. Q is common, p plus q is 1. And the next one. And now t is between 0, t is between 0 and 1. Okay. In this case, what happens? Uh, so probability of that happening is, first of all, the first coordinate must be h. So it is h times something, right? So first coordinate is h, and the second coordinate varies from 0 to t. Okay. That is the inverse image of the set. Yeah. So set of all omega such that x omega is less than or equal to t will involve, of course, it will involve q square, it will involve pq, and it will also involve this. So I write that q square plus Okay, I write PQ, which I already added up till here. And then plus this one, P times T. It's not just T, it's P times T. And which you may simplify. And this is equal to, so I should strictly speaking do it in the next slide, next step, but I squeeze it in. So this is Q plus PT. And of course, it remains the same. 1 less than or equal to T less than infinity, it's again the same. Okay. So I could have just put these two together, but anyway, so and you can draw the graph of this. Let me try and draw the graph of this. Here, the special points are -1 and -half and 0. Okay, now the graph will be drawn in some other distinct color. So up to -1 and not including -1, it is here. And when it is -1, it becomes q square. Okay, I draw that here. This is the graph. And it stays like this up to, but not including when t is -half. And when t is -half, it becomes q. And it stays like this up to some time. And then onwards, it becomes, so here is 1. So I just draw this 1 here. And this is my 1. And it's a straight line segment connecting this and this, because that's what Q plus PT, slope is P, and then onwards it just stays. So this is the graph of y is equal to fx of 12t. It is a t-axis. Yeah, this is how it looks like. Okay. And I want to point out one small feature of this. If you are given the graph, you see somewhere in some interval, if there is a jump discontinuity and this remain, okay, when the jump discontinuity by itself is indication that there is a point mass here or an atom here. Okay, suddenly there is a jump. Okay, so that is the feature of that. That means there is an atom present. An atom simply means that there is a point at which, so probability of x taking that value, let us say x naught, is some positive quantity. Okay, so all right, so I have said enough about this example. Let's just move on. I have several examples to discuss. Can't spend too much time on one particular thing. Yeah. Let us do another example. Maybe this is a much simpler example in some sense. Yeah, okay. Example 2. So blue color. So let us take let omega be is equal to 0 to 100. Okay. And probability that, so probability that I have this, so I write A to B, this is equal to B minus A by 100. So this is what is called uniform distribution or uniform random variable for 0 less than or equal to A less than B less than or equal to 1. Okay, and I am not describing the full P. Okay, so I mean, what do I mean by that? So mind you, omega, this p is a function which assigns real numbers to events. I'm not doing this. I'm not even telling you what this f is. F is the smallest one which contains all these closed intervals or open intervals and so on. So, for example, I'm not telling you what is the probability when you have two disjoint intervals. All right, so let's not worry. Okay, and those will follow from the axioms of probability the moment I tell you what it is on an interval like this. Okay. Uh, Now let us take x, and I should now tell you, having told you what this p is, let us take x and y, two random variables. X of omega is equal to omega, and sorry, y of omega, keep making mistakes. Y of omega is omega square, let us say. And how are what is this fx of omega, fx of t? I prefer to use t, and fy of t. Find. It's a simple enough problem, but let us do this. Fy of t. Okay, what is this? So fx of t, just apply the definition, answer, so solution, whatever. This is equal to probability of all those omega such that x omega is less than or equal to t. Okay. And mind you, the domain for this is whole of real line, not just the interval 0 to 100 or anything. So you must write this, compute it, and write it. Obviously, this is empty set unless t is non-negative. So you put 0. If t is strictly less than 0. And yeah, so if t is between 0 and 100, then what do I get? This set will be okay. So this is all those omega in capital omega. So only the points within 0 to 100 matter. So I will get 0 to t because x omega is omega. So you see, this is just omega is less than or equal to t. So there it is t minus 0, which is just t, and then divided by 100. If 0 less than or equal to t, and this happens up to t equals 1. And after that, of course, it is 1 because it's a whole 0 less than or equal to. Sorry, if t is bigger than or equal to, sorry about that, t bigger than or equal to 100. Okay. Of course, one needs to check that this is indeed, a probability. So on the whole interval, it is of course equal to 1 and so on. So it's clear. Okay. Now what about Fy? That's more interesting. Let us do that. Fy of t, this is equal to exactly the same way you proceed, P of probability of the set. I'll simply write y of omega is less than or equal to t. Okay. And yeah, this is just first step. It's just a definition. Okay. Probability of that. And that is equal to, if t is how is it defined? Omega square is less than or equal to t. Okay. So let us write this. Probability of all those omega in the interval 0 to 1, 0 to 100, such that omega square is less than or equal to t. Okay. So omega square less than or equal to t implies that omega is less than or equal to root of t, because omega is already non-negative. So 0 to root of t. Okay, and this set is root of t by 100. Root of t divided by 100. Okay. If so, here is where I need to be careful. So, uh, if t is greater than or equal to 0, in which, okay, so I need to say this very carefully. So, let me write that here. Mm. If 0 less than or equal to t less than or equal to 100 square, whatever that is 10,000, in which case it is this, and fy of t equals 0 if t is less than 0. What about if this exceeds 100 square and is equal to 1? So now you can write, I'll write this 1 if t is bigger than or equal to 10,000. And here this is root t divided by 100 is 0 less than or equal to t less than less than or equal to 10,000. Okay, so now I have one more problem done. I want to discuss a few more problems. Uh, yeah, some more examples. I have plenty of time, so being okay in terms of time. Uh, Suppose you take, so example. So let me assure you that rest of the course will be concerned with discrete and continuous random variable. It is extremely important you understand these basic examples and concepts, because later on we will go rather fast and not explain too much. So once your foundations or understanding of the basic concepts are clear, we will be able to grapple with the more difficult concepts and theorems and so on, which will come up later in the course. Okay, so it is important that you understand these. I mean, not precisely this particular collection of examples, but basic definitions and concepts which are being illustrated through these examples. Okay, so omega, let us say, is 0 to 1, maybe 0 to r, and r is some number positive. So I want to think of this as an example of uh, where you throw a dart in a circular, in a disk, a circular disk radius r. Maybe let us write radius capital R, I don't know, capital R, okay, capital R. And so the thing is, let us assume that, you know, the um, yeah, so probability of a dart falling into a particular circular disk depends only on the radius. So, sir, okay, so, I'll take back. I want to say more precisely. Probability that a dart will fall at a given point depends only on the radius small r uh, of the circle, which is concentric to the given one, center the same as the previous one. So this is the thing. That is the way the probability is set up. So you may as well think of your omega. What really matters is the distance from the origin. So 0 to r is your omega. You can give a very colorful interpretation of all these little examples, but I will just simply um, get down to business, uh, write down these things. So you see, I want to say probability of the dart falling in the within this interval 0 to r, okay, is something which is a function of r. So 2r minus r square. Okay. Uh, so this is equal to, yeah, actually I just, what is it? Integrated. Yeah. So probability, this is in fact just write 0 to r. This 1 minus, I think 1 minus r. 1, okay, 1 minus t dt. Okay. Yeah. So this is how I want it to be. Uh, now notice that if I put I had r here instead of 1, that's because in my note here I have written 1. So you may just divide by r. Uh, okay, if I do that, r square maybe, I don't know. Divide by r square. So 2r. Okay, I want to just change this because I already normalized it. Otherwise, I should write r by r and then r square by r square. So let me not write that. So just 1. Okay, sorry, I'm changing this. Otherwise, you will have to, wherever you have little r, you have to replace it by r. Not here, but here. Let's just do this normalized 1. It's better that way. So this radius is also 1. Okay, so here I don't need to write this. Okay, sorry, is equal to this. Now what do I get? I get this area, and if you put 0 r equals 1, then I get 2r. So integrated, you will get, and evaluated, you will get this one. There's a
Excuse
2
me,
times.
sir.
There's a 2 times.
Yeah.
Yeah. So when you put r equals 1 in the answer, you get 2 minus 1, which is 1. So it's okay. Everything is okay. But I want to do the example where x, what is x of omega? Okay. This is, let us say, yeah, I can just write whatever I like. 1 by 1 minus omega. Okay. So this is omega is, so x is from, uh, yeah, well, omega to real numbers. Okay, so at omega equals 1, this is not defined. I can just set it equal to 1 if you like. I mean, it doesn't really matter. Omega not equal to 1. Okay, not equal to 1. Not equal to 1. And when omega equals 1, I can just set it equal 0. It doesn't really matter. Omega equals 1. Okay, and this omega is from here to here. Correct? Now find uh, fx. Okay, from r to 0, 1. All right. So this is an interesting function. I just tell you how to go about. I'm not going to complete this problem because I will not have time to discuss other things that I want to discuss today, but I'll just help you set up the problem. Sorry, this is, I always use t here. Doesn't matter what you use.
Sir,
Yes?
so could you explain how you got that probability? I'm a bit confused. Probability is
I'm
0 to
just
R.
declare. So define. I have to have a probability space, no?
Okay, I thought you were using Dart
No,
mode.
I am not computing anything. I am define. Okay.
Okay, okay.
This step is written only to convince yourself that what I have is actually a genuine probability function. See, you need to check that for any r this is positive. How would you know? Well, I write it as 2 times integral 0 to r 1 minus t. Notice that integral 0 to r 1 minus t, this function 1 minus t is positive in the non-negative in this range, right? Okay, so that means that when I integrate a non-negative function, I will get something non-negative. So the probability this is always greater than or equal to 0, and then the probability of the whole space is equal to 1. And I define it only on the interval of the form 0 to r. What about when I have r1 to r2, something like this? And what about if I have, so, when it is R1 to R2, I'll have 0 to R1, 0 to R2 minus 0 to R1. And that is going to be just, same thing. Yeah, you compute it. 2R2 minus R2 square minus 2R1 minus R1 square. That will be this one. And what if it is disjoint union, or what if it is a countable union of intervals? Well, you can just apply the axioms of probability. Okay, we always work with sigma ring, and then anything can be written, as a countable union of. Uh, I mean, First of all, yeah. So I don't want to at this stage go into describing what is a typical element of script f and so on and so forth. Okay, but this determines for you a unique probability, and all I care about at the moment is how it is defined, and it is defined like this. Yeah, this is extremely important. I am thankful for the person who asked this question. It's not like I'm proving anything. I'm just defining it to be like this.
Okay, sir. Yeah, thanks.
Actually, you can, yeah, there's a lot to say. Let's not overload this example with too much of explanation. Yeah, let's compute this one. I'm going to tell you how to compute it. Probably I will not discuss the entire answer completely. Okay, so what is this? uh, Write a typical element T, okay? And what does it mean? You always, even in your assignment, exams, etc., first step of a proof must be a definition, okay? When you make a calculation, write it, even if it is really clear to you, doesn't matter. Write it at least the first 100 times. Once you are familiar with it, you can skip steps. Okay, so this is probability that of omega such that x omega is less than or equal to t. And this is equal to, sorry about it, probability of this set omega. After this stage, you may first simplify this and then plug in and so on. Anyway, I write it. So x omega is what? 1 by 1 minus omega is less than or equal to t. Now, what is this set? So I write here omega such that omega in which interval? Let us write that. That is 0 to 1. Okay, 0 to 1. And now you just cross multiply, simplify, and so on. I will get, when I cross multiply, 1 less than or equal to t minus t omega. So you take t omega to this side, and then the constant to the other side. If I did that thing correctly, okay, let me write t less than or equal to, sorry, okay. Yeah. 1 is less than or equal to t minus t omega. This is the set, ignore that bracket there. So omega 0, 1. So you bring this to this side and this to this side, and then you write omega is less than or equal to 1 by, no, t by uh, t minus 1 by t. I'm now dividing by t. If t is positive, inequality is preserved. So you have to pay attention to this. If t is greater than 0. Okay. All right. What if t is less than 0? You have to wonder about that. So if t is less than 0, t omega is less than 1 minus t minus 1. Okay. So, so I have, so if, omega will be bigger than or equal to this, t is negative. This is not possible if t, so if t is less than 0, you will not have omega in omega satisfying this equal to empty set. Check this if t is less than 0. Okay, that much is clear to me, seems to me. You see, this is omega is a fraction. This will be a fraction of t. And this is t minus 1 is even less than t. So you see, if t, how can that happen? Yeah, that's not possible. Okay, so this is empty set if t is less than 0. So we may as well assume that t is positive. In fact, if t is less than 1, if moment t is positive, denominator is positive, and this one tells me that if t is if t is, well, actually t is less than or equal, I don't know. So if t is less than 1, then this is negative, and therefore it's, anyway, this is empty set. Okay, so let me go to the next page. Otherwise, well, therefore I assume t, so assume t is bigger than or equal to 1. In fact, if it is bigger than 1, then it's just a single point, and when I compute the probability for a singleton, you can check it is 0 because anyway it's given by integration. So for a single point it's 0. And then what can I say? So assume that t is therefore bigger than 1. Okay, in this case, what will happen? Then omega, this set omega such that omega satisfies that inequality is less than 1 by 1 minus t. This is equal to set t omega, sorry, this is less than or equal to, did I write that right? 1 minus omega is less than t. Reverse the role here. I'll write xt less than or equal to this. So x omega less than or equal to t such that this is omega is less than or equal to t minus 1 by t. Okay. And now it's easy to compute what it is. Therefore, f of x of omega is equal to probability of the set 0. Okay. T minus 1 by t, which you can compute. Of course, yeah, this is allowed. Okay, so this you can compute. I'm not going to compute this. You can complete this. This, of course, here you are assuming t bigger than 1. So, of course, sorry, here I should write t, it's not omega. So you must now ultimately write this. I'm not going to complete this. what happens if this is less than or equal to 1 and this is bigger than or equal to 1? This you will complete at home, left as an exercise and complete, incomplete. Okay. Yeah, so what is the next thing I want to do? Okay. Um, I uh, I'm going to do a similar problem, but this time I'm going to change the probability function. I wanted to do another problem. Okay, so let me do this. So consider, so this is also example 4. So let again omega equal to 0 to 1 and p of uh, 0 to, let us say, x maybe is equal to uh, just x. Okay. And this defines, so defined here. Define this and now define x of omega is equal to yeah, we want to do the same thing because I want to keep the calculations. I can just borrow from the previous thing, at least part of it. Now, so up till this step, it's going to be the same calculation. Okay, it is only this step which I have not completed. You are going to do the calculation that involves probability. But now we can borrow that and write what is, so question is find fx of t. Okay, uh, is x continuous? So that is, this is the same thing by definition, the same thing as does x have a density function? Density function. Little f is the question. So if so, find it. Find it. Okay. So as I said, what is this one? Fx of t. This is equal to yeah. So this is a probability of all those omega in omega such that x of omega, so 1 minus omega is less than or equal to t. Okay. So this is equal to empty set. So probable. So this is 0 if t is, so we already had that here. I could have written that. Okay, let me write one more step just for sake of completeness. T minus 1 by t. For the sake of clarity and completeness, let me write that probability of omega such that 0 less than or equal to omega less than or equal to t minus 1 by t. T is bigger than or equal to minus 1. Okay, and which is, what is it? So we know what is the probability of the interval 0 to x, and t is bigger than or equal to plus 1. I'm sorry, plus 1. Erase that and write bigger than or equal to 1. Okay, and in that case, what is the probability? So whatever this is that interval 0 to t minus 1 by t. Okay, and that is just x t minus 1 by t. T minus 1 divided by t. Mhm. If t is equal to, t is bigger than or equal to 1 and is 0 if t is less than or equal to 1. Yeah. Can you find some function? So this is uh, fx of t. So the question is, so whether x is continuous random variable or not will depend on the following. So uh, so question is, does there exist f of t such that integral uh, integral okay minus infinity to t f of u du is equal to this function ft, like fx of t. I will drop x once. Okay, so this is a question. Let us write that question here. 1 minus, so t minus 1 by t, that is 1 minus 1 by t. So this you can, okay. This is the case if t is bigger than or equal to 1, 0, otherwise, no, 0 if t is less than 1. So f of, so you just have to, so you see, what is it that you are solving? By fundamental theorem, if f is indeed this one, when I take the derivative of f, I should get little f. Okay, so I take the derivative of this. Uh, yeah, so f of t is equal to f dash of t. If t is bigger than or equal to 1, 0 if t is less than 1. So you can, and f need only be continuous, f need not be differentiable. So this suggests that f of t has to be equal to 0 if t is less than 1. And now find the derivative. This is 1 by t square. Sorry, 1 by t square, no? If t is bigger than or equal to 1. And now compute it, just to be sure. What is integral minus infinity to infinity, sorry, not infinity, but t of fu du? This is equal to, so integral 1 to t, t bigger than 1. If t is less than or equal to 1, this is 0. So let t be bigger than 1. Just go directly to the thing where the 1 by t square, you compute it, dt. 1 by u square du. This is equal to, did I make a mistake here? No, I think so. Yeah, when I integrate it, I get minus u square minus 1 by u between 1 and t. This is equal to, so 1 by 1 minus t. This is okay. This is f of. as required. That's it. Finished. No? So if it exists, this has to be this. So this is a function. Then we are done. I have some more questions to discuss. Uh, yeah, okay. So, exercise. So, suppose that this is from the book that f g are density functions of distribution functions. Just say distribution functions, let us say functions f and g. Okay, show that for any lambda greater than 0, for any lambda such that 0 less than lambda less than 1, lambda times f plus g times, 1 minus lambda times 1 minus lambda times g is the density function of a random variable. Density function of a random variable. So here, so density function for distributions, these are, so how do we do this? You just have to check that, you, uh, so define, define. So instead of saying distribution, a random variable, just say of a distribution, that's enough for us. So, yeah, so you define what the most natural thing and then check that this is indeed a distribution function. So the h of t is equal to minus infinity to t lambda times ft plus 1 minus lambda times, sorry, here I should write u, keep making mistakes like that. 1 minus lambda times g of u du. And when you do this, you get, use the fact that f and g are distribution functions. So I get here lambda times f of t plus 1 minus lambda times g of t. Okay. And now the question is this a distribution? So I am taking a convex linear combination of f and g, capital F and capital G. Is that a distribution function? You have a set of axioms, no? For some function to be a distribution function, you check that. Check that H satisfies all the requirements for it to be a distribution. That's it. What about, the question is, with the same notation, what about ft, f times, okay, f times g? This is a question. Okay. Now, you see, you should expect this to fail. Because you see here you use the fact that integration is linear, but it is not going to be multiplicative, and therefore it should fail. So I will just simply say try f square even. Okay, show that for some f square is not a density of any distribution. You can try and show that. And one of the things that you can try and show, how do you show something is not? Well, I mean, for a specific f, you may be able to write h. You can, after all, integrate some nice function. You may be able to find h, but that h may not satisfy. So that's one way to check it. So I've given you enough hints. Try and do this problem. This is an exercise. Okay? Exercise. Yeah. I have still a few more minutes. Let me try to squeeze in one more problem. In the meantime, I suppose I have. Okay, this uh, this question is of a theoretical nature, so I will try and do this. Maybe I take a new page. So suppose that, yeah, I think maybe in the problem, I just 1 second. I may do something and I lose connection as a problem. 1, 3. I'll check that problem screen. Okay. I don't know where that page disappeared. Okay. Are you able to see the this Wacom board I am using? I hope.
Yes, sir.
Yeah. Okay. So this is a question. Yeah, it will take 5 minutes to state this question. It's a long one to state. Okay, suppose x is a random variable with a distribution function f. Okay, so now we have a sequence of numbers indexed by integers, m be in here, be increasing. What does that mean? So when you think of it as a function from, okay, integers to real numbers, that's an increasing sequence of real numbers. So strictly increasing, let us say, strictly increasing sequence of real numbers. Okay. Now what you do is define a function g of x. G of x is equal to so what is that? Yes, I need to check that. G of x is probability. Okay, fine. Yeah, this is probability that x is less than or equal to am. If am minus 1 less than or equal to x, strictly less than am. Okay. Yeah. Let us define it this way. There are then this is a distribution. Then G is the distribution function of a discrete random variable. We may call it Y maybe. Okay. Of course, Y depends on the sequence A. Y is equal to Y of A. Okay. Now the problem is what happens if supremum of these distances. I mean, you see, the AMs are certain discrete set of numbers. Some countable set of numbers. And I want these distances, AM, successive ones, AM minus 1. In fact, I can put round bracket, M, just go to 0. So this is a supremum over M. When I take this in integers, I get a certain real number. And that number, I want it to go to 0. Then I will get various, as I allow this, I get various G's. Okay. How is that related? What happens? Meaning, what is the relation between what happens to G if this goes to 0? So, this is a question. I don't have time to discuss this completely. I'll let you think about it. The important thing is, first let us check that this is a discrete random variable. Is it clear that it's a discrete random variable? Well, it takes only countably many values, no? And it is non-zero, when it is greater than or equal to 0. So if at all it's a distribution function, it has to be a discrete, of a discrete random variable. The thing is, um, uh, what about, what about limit? So you see, this is one thing we need to worry about. So part of the answer. So I'm just checking that y is a discrete random variable, because so I want to see so G takes values in a countable set. Namely, so this is solution. I will be unable to complete it, but a countable set, namely, what is that set? The set is this probability that x is less than or equal to AM and m in integers. Okay, so that is already done. What about limit m going to infinity? I didn't say that here. I should have said that, or maybe not required even. It could accumulate. Okay, minus 1. Yeah, I should have said that maybe. Because the book was concerned only about the second thing, it didn't matter for them, but let's assume that. So here, let me squeeze in strictly increasing sequence of real numbers. Let me squeeze in here such that limit m going to infinity plus infinity am is equal to plus infinity, and limit m going to minus infinity am equal to minus infinity. Let's assume that. Then I can say the following. So here you can just check that if you just limit n goes to plus infinity, g of x goes to plus infinity, g of x is equal to plus 1, and limit x goes to minus infinity, g of x is equal to 0. Okay, is that clear? Yes? Yeah. So therefore, G is the distribution function function of a discrete random variable. Yeah, I'll stop here. So the thing is, you draw the, so to those, I mean, you may explore the answer for yourself for the remaining part of the question by just analyzing, drawing the graph. Okay, I just do it. So AM minus 1, AM, and then how will the graph of, so F may look something, we don't know what F is, but maybe assume at the moment just for a convenience. Otherwise, I'll not be able to draw anything. So some continuous part of the curve, this is graph of y is equal to f of x. Whereas this fellow G will have, because it's the graph of a discrete random variable, it will be like a step function. Okay, so it will look like this. I took two successive ones, and okay, here this is this, and maybe here something like this, and this is a point corresponding to AM. Okay, so this is how the picture looks like. Now imagine what will happen if the numbers AM minus 1 and AM come very, very close to each other. So it doesn't look like a monotone function. That's because my picture was bad, but you understand. It's a, yeah, so let me correct that, and with that I will stop. So, okay, I'll stop here. Stop sharing. Okay, so we will continue our discussion, but in the meantime, you can try. It's a nice and interesting exercise. It will help you understand connection between discrete random variable and continuous random variable and so on. So, in fact, f is given to be an arbitrary, not even told, you are not even told that it's a continuous. It doesn't really matter. F is an arbitrary distribution function. Okay, we'll stop here for today. Sorry about exceeding the time. All right. Yeah, bye.
Thank you.
Yeah, welcome.
Thank you, sir.